Hello everyone, we are Group 11 from L Division with the topic IEEE Standards for Floating Point Representations. The subtopic which we will cover are data type representation by Prathamesh, that is me, floating point representation introduction by Vedant, basic terms for floating point representation by Shrihari, IEEE 754 floating point representation by Shreya, example for floating point representation by Moin, and conclusions by Mrunal. So basically there are two types of data type representations, namely fixed point number and floating point number. The main difference between the fixed point number and floating point is that the fixed point has a specific number of digits reserved for the integer part and fractional part, while the floating point does not have a specific number of digits reserved for the integer part and fractional part. Fixed point and floating point are two ways of representing numbers. In fixed point, there is a specific number of digits to represent the integer section and fraction section. In other words, there is a fixed number of digits for each portion, even though the number is very large or small. On the other hand, in floating point, there is no specific number of digits to represent the integer section and fraction section. Floating point representation can cover a large range or number even when compared to fixed point. Fixed point representation is used to present a limited range of values. On the other hand, floating point representation is used to represent a wide range of values as there is no restriction for the range of the values. As for performance part, fixed point representation performs better than floating point representation as it is for a fixed number of digits. For the part of flexibility, fixed point representation is less flexible than floating point representation.
Introduction to floating point representation. The description of binary numbers in the exponential form is called floating point representation. The floating point representation breaks the number into two parts. The left hand side is a signed fixed point number known as mantissa, and the right hand side of the number is known as exponent. The exponential inherent in floating point computation assures a much larger dynamic range, the largest and the smallest numbers that can be represented, which is especially important when processing extremely large data sets or data sets where the range may be unpredictable.
Now we see what is floating point representation, but before learning it, you need to understand these three parts. That is, what is mantissa, what is base, and exponent. Now suppose you have a number, suppose 6 into 10 raised to 3 is a number, and you may want to understand what is a mantissa in this number. Then 6 is a mantissa, base is 10, and exponent is a 3. Similarly, if you want to find what is a mantissa, base, and exponent in a second example, then in this example, the number is 13 into 4 raised to 8. The mantissa is 13, base is 4, and exponent is 8. Now if you see the third example, then it is slightly different. In this example, first you have to convert the given number into 10 to the power, and after doing this, the number looks like this. Now we can easily find out what is the mantissa, base, and exponent. So in the example 3, if you see, the mantissa is 1, 2, 3, 4, 5, base is 10, and exponent is a minus 2. So these are the some basic terms that you need to know before learning floating point representation.
It wasn't until 1985 that the Institute of Electrical and Electronics Engineers defined the standard format for floating point binary. The standard addressed many problems found in the diverse floating point implementations that made them difficult to use reliably and portably. Many hardware floating point units nowadays use IEEE 754 standard. So let us see IEEE 754 standard for representing floating point binary numbers. IEEE 754 standards describe floating point formats, a way to represent real number in hardware. At least 5 internal formats for floating point numbers are representable in hardware targeted by MSVC compiler. The compiler only uses two of them. Those are single precision format and double precision format. The simplest way to distinguish between single and double precision computing is to look at how many bits represent the floating point number. For single precision, 32 bits are used to represent floating point number, and for double precision, 64 bits are used to represent floating point number. Notice that sign bit is the leftmost bit followed by 8-bit exponent and then 23-bit mantissa. In double precision, single sign bit on the left followed by 11-bit exponent and then 52-bit mantissa, giving a total of 64 units instead of 32. Single precision floating point format uses 32 bits of computer memory and can represent a wide range of numerical values, whereas double is mostly used for calculations in programming to eliminate errors when decimal values are being rounded off.
Take a look at the example to understand the IEEE format. The example is represent 102.250 in single and double precision format. So the first step is converting the number to its binary form. The binary form of 102 is 1100 and of 0.250 is 01. So our number will become 1100 So this number will be used in the further stages. So let's move on. The next step is to normalize the number. The normalized form of the single precision format is this 1.1 into 2 to the power e minus 127, and of the double precision format is 1.n into 2 to the power e minus 1023. As our number is 110011 it can also be written as 11001101 into 2 to the power 6. As here the base is 2, it is 2 to the power 6. If it was 10, we would have written it as 10 to the power 6. From this we can see that our n will become 1001101. Just keep it in mind, we will need it in the later stage. So the third step is comparing our number with the normalized form. So in the first part, we will compare it with the single precision format's normalized form. For that, the e minus 127 will be equal to 6 by comparing them. So e, which is exponent, will be equal to 133. Now let's take the binary form of that e, which is of 133. The binary form is 100001001. So let's move on to the filling the table. For sign, we will put 0 here because our number initially was positive, so we will write it 0 in the sign column. In the exponent column, we will put the binary form of the e. For mantissa, there will be the n value, and the others after that will be 0 to complete the size of the mantissa, and that those zeros will not affect our representation. So this was the our number in single precision format. Let's move on to find how the double precision format will look. For double precision format, e minus 1023 will be equal to 6, and so the e will become 1029. Just like the previous step, we will get the binary of that e and put it in the table. So the sign here will be the same 0. The exponent will be the binary form of 1029, which is from here, which is copied, and from mantissa we will to the mantissa we will put the n value, and others will be 0.
Here I will be covering conclusions of floating point representation. So first one is the IEEE 754 standard is a standard for representing and manipulating real number in computing, or you can also say that is the most common representation today for real numbers on computers, including Intel based PCs, Macs and mostly unique platform. There are several ways to represent floating number point, but IEEE 754 is the most efficient in most cases. Now moving forward, it defines the format of representing numbers, the range of numbers that can be represented, and the operation that can be performed on these numbers. Further, the IEEE 754 standard is used in most modern computers and is de facto standard for representing and manipulating real numbers in computing. Basically, de facto standard is one that has become accepted in practice but has not undergone any formal process to obtain consensus and may not even have publicly available documentation. Thank you for being a good listener. Hoping for your positive responses. Thanks once again.